The Jordan-Holder theorem that we've been studying in the last few lectures is what is known as the Jordan-Holder theorem for modules. There's a very similar theorem which also holds for groups. So I'm going to take a few minutes to explain this variant of the Jordan-Holder theorem, the Jordan-Holder theorem for groups. Most of the ideas in the proof are very similar, and so I won't go over the proofs again. However, working with groups creates a few difficulties which need to be addressed. I'll just tell you what they are. Okay, so firstly, let's come to the definition of a simple group. So we said that a module is simple if it doesn't admit any non-trivial proper submodules. For a group, we need to be a little more careful. The main point being that if you have a group and a subgroup, you cannot always define a quotient. In order to define the quotient of a group by a subgroup, you need the subgroup to be normal. That's when multiplication on the group descends to a well-defined multiplication on the cosets. So a group is said to be simple if it has no proper non-trivial means the trivial group is just the group with only the identity element, no proper non-trivial, and the most important word here is normal subgroups. Right, so the most common example of simple groups are the alternating groups an for n greater than or equal to 5. And these, you can see, do have subgroups. Any element of such a group will generate a cyclic subgroup, but there are no normal subgroups in these groups. Okay, and so if a group is simple, then it doesn't have any non-trivial proper normal subgroup. If it's not simple, you can find a non-trivial proper normal subgroup, and then you can look at that normal subgroup, and maybe you can try to look for its normal subgroups, or you can look for normal subgroups in between the group and the normal subgroup. But in this way, you can construct the analogs of what we had called composition series. They are also called composition series for groups. So definition, again, we need to make a slight change. So a composition series for a group G is a sequence of subgroups which I will call G equal to G0 containing G1 containing G2 going up to Gn, which we will assume to be 0, such that, and now we need to add this normality condition, Gi plus 1 is normal in Gi for each I going from 0 to n minus 1. Now, because of this normality condition, we can define the quotients. So the quotients of the series are the groups Qi equal to Gi modulo Gi plus 1 for I goes from 0 to n minus 1. Okay, and these make sense because Gi plus 1 is normal inside Gi. And now we can also define equivalence of composition series. So we'll say that two composition series Gi I equals 0 to n and Hj j equals 0 to n are equivalent, and this definition is identical to the definition in the case of modules. If firstly m is equal to n, and secondly there exists a bijection sigma from 0 to n minus 1 onto 0 to m minus 1 such that gi mod gi plus 1 is isomorphic to the group h sigma I mod h sigma I plus 1. And with these slight modifications in place, Schreier's theorem still holds. So we have Schreier's theorem for groups. And it says that given two composition series, sigma 1 and sigma 2 for the same group G, there exist refinements sigma 1 prime and sigma 2 prime of sigma 1 and sigma 2 respectively. So maybe I'll just say respectively, such that sigma 1 prime is equivalent to sigma 2 prime. And the proof of Schreier's theorem is very similar to the proof of Schreier's theorem for modules. We just need to be careful to make sure that whenever we take quotients, the subgroups involved are normal. So you need to make that check at each stage. But it's not difficult, and I'm sure if you were to, and I would strongly advise you to try to write down a proof of Schreier's theorem for groups by yourself. So the argument is exactly the same. You define sigma 1 using sigma 2, and you define sigma 2 using sigma 1. And then we can talk about the Jordan-Holder theorem for groups. So this says that any two Jordan-Holder series for a group are equivalent. Okay, this could have been stated for modules also in this way. Basically, we're not concerned with whether there exists a Jordan-Holder series or not. We're saying if there are two Jordan-Holder series, which means that they exist, then they are equivalent. And this is a direct consequence of Schreier's theorem. But hang on, I didn't explain to you what a Jordan-Holder series is, but I'm sure most of you can easily guess. So let's just define a composition series gi I goes from 0 to n is called a Jordan-Holder series if it does not admit a strict refinement. But maybe I'll just state it in another way. If gi mod gi plus 1 is simple for every I, and this implies that the GIs are distinct. Okay, so one more thing maybe I should say is that a group is simple if it is non-trivial and it has no proper non-trivial normal subgroups. So we do not consider the trivial group to be simple. So it's called Jordan-Holder FGI. So this means that the GIs are distinct and that you cannot further refine this composition series by inserting new terms in between. And so just like before, these are composition series which do not admit strict refinements. And so now the Jordan-Holder theorem says that any two Jordan-Holder series for a group are equivalent. And the proof is exactly the same as for modules. And so just philosophically, what does this say? So in some sense, it says that okay, so let's just talk about finite groups. Because of finiteness, finite groups always admit Jordan-Holder series. But there are infinite simple groups and there are infinite groups which admit Jordan-Holder series as well. And so every finite group has a Jordan-Holder series where the quotients are finite simple groups. And this is a very important class of groups because of this theorem. It says that finite simple groups are the building blocks of all finite groups. However, the story doesn't end there. We do today have a classification of all finite simple groups. However, we are far from having a classification of all finite groups. Because even if we know the finite simple groups in the Jordan-Holder series, we do not understand all the different ways of putting them together to construct groups up to isomorphism. So it breaks down the problem of classification of finite groups up to isomorphism into two parts. One is the classification of finite simple groups up to isomorphism, which, although a major mathematical endeavor spanning several decades and many mathematicians, has been solved. And the other part is how do you put together finite simple groups, or given a sequence of finite simple groups, how do you construct all the isomorphism classes of finite groups which have that sequence as its or that set maybe as its set of quotients for its Jordan-Holder series. So we do not know how to answer that second question. But nevertheless, the Jordan-Holder theorem for finite groups is a major theorem in group theory.